Hello everyone, let's begin the new chapter Semiconductor Electronics. The word semiconductor is made up of two parts, semi and the conductor. It indicates that it's neither a good conductor nor a good insulator. If the temperature of semiconductor is increased, it will try to behave as a conductor, and if the temperature of semiconductor is decreased, it will try to behave as an insulator. Here is the index of the lecture. First of all, we will talk about the vacuum tubes and their demerits. Then we'll go to the introduction of the semiconductors. After that, we'll classify the semiconductors in two categories, the elemental semiconductor and the compound semiconductor. Then we'll go through the energy band diagrams. And based on the energy band diagrams, we'll classify the materials in three categories: the conductors, insulators and semiconductors. Then we will go through the intrinsic semiconductors as well as the extrinsic semiconductors. In this video, you will find various unique concepts regarding the semiconductor. One thing I can promise you, if you go till the end of the video, you will master all these concepts. So let's begin. The devices in which the controlled flow of electrons can be obtained are the basic building blocks of all electronic circuits. Before the discovery of the transistor in 1948, such devices were mostly the vacuum tubes. The vacuum tubes are of type vacuum diode, the vacuum triode, the vacuum tetrode and vacuum pentode. Vacuum diode means there will be two electrodes, cathode and anode. Vacuum triode means there will be three electrodes. So on, tetrode will have 4 electrodes and pentode will have 5 electrodes. These vacuum tubes are also known as the valves because the electrons can only flow from the cathode to anode. But the issue with the vacuum tube devices is they are bulky, more power consumption. They operate generally at the high voltages of the order of around 100 volt. And these devices have limited life and low reliability. Why vacuum is required between the cathode and anode? If the vacuum is absent and there are air molecules present, then electrons might collide with the air molecules and lose their energy. The seed of development of the modern solid-state semiconductor goes back to the 1930s. And it was realized that some solid-state semiconductors and their junctions offer the possibility of controlling the number of the charge carriers as well as their direction of flow. Here are few advantages of the solid-state semiconductors. They are small in the size. They generally operate at low voltages. They consume less power. They have a longer life and high reliability. Simple excitations like light, heat or small applied voltage can change the number of charge carriers in the solid-state semiconductors. The electrons flow inside the solid itself, so no requirement of the vacuum. That's why their size is small as compared to the vacuum tubes. Semiconductors are the basic building blocks of all modern day electronic circuits or gadgets such as the mobile phone, the laptop, the computer, the iPad, the satellites, the radars. There are other numerous daily life applications such as the light emitting diode, such as the solar cells, the amplifiers, the rectifiers, electronic switches, etc. If I ask you one thing, the first computer which was invented and your mobile phone, which is more powerful? Obviously, your answer will be your mobile phone. What's the reason behind that? The reason behind that is the development of the solid-state semiconductors. The solid-state semiconductors are faster and smaller. Here we can see the classification of the semiconductors. They are broadly classified into categories: the elemental semiconductors and the compound semiconductors. The elemental semiconductor means there will be a single element present, such as if we talk of the silicon or germanium, then in the silicon semiconductor all the atoms will be of the silicon only, as well as if we talk of the germanium semiconductor, all the atoms in that semiconductor will be of the germanium only. They are also known as the pure semiconductors. Then there comes the compound semiconductors. The compound semiconductors is further divided under few categories: the inorganic, organic, as well as the organic polymers. Our next topic is the energy band diagrams of the solids. Here you can see a famous statement regarding the energy band diagrams by the year 2000 Nobel laureate Sir Herbert Kromer. This statement shows that for understanding the semiconductor devices, we should be knowing the energy band diagrams very well. So let's start. Next topic is the energy band diagrams of the solids. For an isolated atom, the electronic energy levels are far apart and widely separated. During the formation of the crystals, when the atoms approach each other, the outermost electrons will interact and their energies might increase or decrease. The reason behind that, every electron sees a unique neighborhood. We know that at room temperature in a crystal the atoms are vibrating. So the pattern of vibration around one electron is not exactly similar to the pattern of vibration around the other electron. That's why they all will have the different energy levels. So let's have a look at this. On y-axis, suppose we consider the energy, and on the x-axis we are taking up the number of atoms. First of all, we talk about a single isolated atom. In a single isolated atom, we know that the energy levels are discrete. So the energy of the first orbit, let's say we indicate here as E1. The energy of the second orbit we indicate here as E2, and the energy of the third orbit we indicate here as E3. For E1 there will be a discrete energy level, as well as for E2 and as well as for E3 there will be the discrete energy levels. Now we consider a case of two atoms. The outermost electrons will interact first, and due to the interaction between the electrons there will be the formation of bands. Since we have two atoms, so here we will have two energy levels. Same will happen for E2 also. For two atoms you will get two energy levels. Same happens for E3 also. There are two different atoms, so two different energy levels. Suppose next case we consider we have three atoms. When the three atoms will interact, then here we will get three different energy levels. So we are plotting them here, three different energy levels. Same will happen for E2 also, three different energy levels, as well as here. The bandwidth of these energy levels or these bands will depend upon how tightly the electrons are bound with the nucleus. Here the bandwidth is less. The reason behind that, these electrons are closer to the nucleus, so they are tightly bound. That's why the bandwidth is less. The outermost electrons, they are a bit loosely bound, so the bandwidth is more. Suppose next we consider we have n atoms, and n is a very large number. Here will be n energy levels. But since the number of atoms are large, so you will have the large number of energy levels in a small space, and this will look like something continuous. From far away, if we look into this, we will see a continuous variation of the energy, but actually here we have the discrete energy levels. Same will happen for E2. There will be a large number of closely spaced energy levels, and we can term that as the energy band. If someone asks you how many energy levels are actually available, then our answer should be we have here n energy levels. We have seen that if there are large number of atoms, then there will be a large number of energy levels in a given energy band. So let's observe it through a question. The density of sodium is given to us 968 kg per meter cube, and we have to find the number of energy states in 3s band per cubic meter. So let's start the calculation. To solve the question, first of all, we will find the number of moles. If we know the number of moles, we can multiply the Avogadro number with that and we'll get the number of atoms. Suppose we get n number of atoms, then we know that there will be n number of energy states available. So let us start the calculation. Number of moles per cubic meter is equal to mass divided by molar mass divided by volume. The mass by volume is the density, and density is given in the question 968 into 10 to power 3 gram per meter cube divided by the molar mass is 22.989769 gram per mole. This will give us the number of moles in a cubic meter. Now we can find the number of atoms per cubic meter. So if we put this in a particular bracket, then this bracket multiplied with the Avogadro number will give us the number of atoms per cubic meter. Hence, we know the number of energy states per cubic meter. Let's do that calculation here. 968 into 10 to power 3 divided by 22.989769 into 6.0224076 into 10 to power 23. These many energy states will be actually available. This is the value of the Avogadro number. Now, the question is asking, out of these many energy states, how many are empty? For that, let's have a look at the electronic configuration of the sodium. For the sodium, the electronic configuration is this: 1s2, 2s2, 2p6 and 3s1. If we look at the 3s, it is half empty. Actually, it can accommodate 2 electrons, but there is only 1 electron present. So out of these many energy states, actually the half will be empty. Let's do that calculation. Number of empty energy states in 3s band per cubic meter will be equal to half of this number. If you do the calculation, this number comes out to be 507.13 into 10 to power 26. And the empty energy states will be exactly half of this number, 507.13 into 10 to power 26. The answer will be 253.56 into 10 to power 26. Let us see the energy band representation of the solids. The bands where the valence electron resides is known as the valence band. And suppose we draw this picture at 0 Kelvin. At 0 Kelvin, all the valence electrons are bonded with their respective nuclei. So we have a large number of energy states in the valence band, and each energy state will have 2 electrons. And where the conduction electron resides, that we show as the conduction band. At 0 Kelvin, no electrons are free. So the conduction band is totally empty. In between the valence band and the conduction band, we define energy gap Eg. The lowest level of the conduction band is shown by Ec, and the highest level of the valence band is shown by Ev. And this forbidden energy gap, or simply energy gap, is equal to Ec minus Ev. Let's talk about this energy gap Eg. Eg is inversely proportional to the lattice constant. If the atoms are closer, the energy gap will be more. Eg slightly varies with the change in temperature, so Eg is proportional to 1 by temperature. As the temperature increases, the energy gap decreases. No electrons can exist in the energy gap. Few books name it as forbidden energy gap also. Now let's talk about the bandwidth of valence band and the conduction band. The bandwidth of the conduction band or valence band depends upon how strongly the electron is bound to the atom. If the lattice constant is small, it means there is less space and the electrons are closely bound with the atom. So the bandwidth of conduction band or valence band is directly proportional to the lattice constant. Smaller the lattice, we will have the smaller bandwidth, because in a small space we need to accommodate the given energy levels. Classification of the materials based on the energy band diagram. First of all, we will be talking about the metals. Here are the two possible pictures of the energy band diagrams of the metals. In the first picture, the valence band can be partially filled as well as the conduction band. So by absorbing some energy, the electrons can go from lower energy level to the higher energy level and can make the conduction feasible. In the second diagram, the lower energy level of the conduction bands and the higher energy level of the valence bands are overlapped. So the electrons from valence band can easily move in the conduction band. In this case, the energy gap is 0. The resistivity of the metals is very low and the conductivity of metals is very high. If electric field is applied, then electrons move from lower energy level to the higher energy level, and this gives the rise to the current. Now let's talk about the insulators. The outermost electrons in the insulators are very tightly bound with the atom. So there are no free electrons. That's why they cannot conduct the electricity. Here you can see the energy band diagrams of the insulators. The energy gap between the valence band and the conduction band is more than 3 electron volt. So by absorbing some thermal energy, the electrons cannot jump to the conduction band because the energy gap is large. For practical example, we can consider the diamond. The diamond has the energy gap of around 6 electron volt. So at the room temperature, if some thermal energy is given to the electrons in the valence band, they cannot jump to the conduction band. The resistivity of the insulators is very high and their conductivity is very small. Let's talk about the energy band diagrams of the semiconductor. For a semiconductor, the energy gap is less than 3 electron volt. Such as, for example, the silicon has the energy gap equal to 1.14 electron volt and for germanium the energy gap is around 0.72 electron volt. Due to the small energy gap at room temperature, due to the thermal agitations, few valence electrons can break their bonds and enter to the conduction band. These electrons can move freely in the conduction band and hence they are known as the conduction electron. Actually, the number of such electrons is small as compared to the metals. That's why the conductivity of the semiconductors is small or less as compared to the metals, as well as their resistivity is also less as compared to the insulators. If we talk of the electrical resistivity and the electrical conductivity of the semiconductors, here are the values. If the temperature is increased, the drift speed and the mobility of charge carriers decreases, but the increasing temperature leads to breaking of more covalent bonds and the number of charge carriers increases. Thus, on increasing the temperature, the resistance of a semiconductor decreases. Hence, the temperature coefficient of the resistivity will be negative for the semiconductor. For silicon, the average value is around minus 0.07 per Kelvin or per degree centigrade. Let's talk about the intrinsic semiconductors or the pure semiconductors. Only a single kind of atom are present. It means there are no impurities. For example, if it is silicon semiconductor, all the atoms will be of silicon only. For silicon or germanium semiconductor, I am making a 2D representation of the crystal lattice. Here, silicon or germanium have 4 electrons in their outer orbit. It is a simple representation to understand the semiconductors very well. To complete the octet, they require 4 more electrons, and which they can obtain through the covalent bonding. The covalent bonds here I am showing with the dotted lines. Now, the outer orbit finally has 8 electrons. 4 electrons were already present and 4 every atom is getting via the covalent bonding. The covalent electrons can shuttle back and forth between the two atoms. Suppose if this electron is the covalent electron, it can shuttle back and forth between these two atoms. These dots, the small red dots, they are basically indicating the electrons in the outer orbit of the silicon or germanium atom. It's a simple crystal lattice structure. At low temperature, all the bonds are intact. So suppose we are making this diagram at 0 Kelvin. Then all the electrons are bonded. There are no free electrons. At 0 Kelvin, all bonds are intact. If all bonds are intact, it means there are no free electrons. If there are no free electrons, it means there is no conduction and the resistance is infinite. So the pure semiconductors at 0 Kelvin will behave as a perfect insulator. Let's draw the energy band diagram of the pure silicon at 0 Kelvin. Here is the valence band, and we know that at 0 Kelvin all the electrons are bonded. So the valence band will be completely filled. Above the valence band, there is some energy gap. In this energy gap, no electrons can exist. and up here lies the conduction band. Since there are no free electrons in the crystal lattice, so the entire conduction band is empty. All the energy levels are vacant. Let's write that here, that conduction band is empty. This diagram is made at 0 Kelvin. Now suppose the temperature increases. As the temperature will increase, few covalent bonds will break and the electrons will become free. As the temperature increases, few covalent bond breaks and electrons become free. Let's see that here. Suppose this covalent bond is breaking and the free electron leaves a vacant site, and that vacant site is known as a hole. Hole is an imaginary particle. Just the absence of electron is known as a hole. The vacant site in the valence band is known as hole. Again, you should focus on this, that it's an imaginary particle. Hole is an imaginary particle. But if you assume it, then explaining the concepts of semiconductor becomes super easy. That's why we imagine it. The effective charge, why we use the term effective? Actually, hole doesn't exist. The effective charge of hole is plus E, because it is the absence of the electrons. So the effective charge is plus 1.6 into 10 to power minus 19 coulomb. The effective mass of hole is greater than the mass of electron, and the mobility of holes is less than the mobility of electrons. So basically we have two kind of charge carriers in the intrinsic semiconductor, holes as well as the free electrons. Now as temperature is increased, what happens to this energy band diagram? Let's have a look. Same conduction band and valence band will make again and will show what difference occurs when the temperature is increased. So up here is the conduction band. This is the energy gap. No electron can lie here in this energy gap. Since there are free electrons available in the lattice, it means there will be few electrons present in the conduction band. In the valence band, there will be few holes present. Where the bonds are broken, there we will get the holes. So here is a hole. There could be more holes. It's a simple representation. When the temperature is more than 0 Kelvin, the valence band has few bonded electrons and there are few holes. Now let us discuss how the movement of the hole and electron takes place. Due to the thermal agitation, few more covalent bonds can break and then few more electrons are free. These free electrons roam inside the crystal lattice. So suppose due to the thermal agitation, one more bond is breaking and the electron becomes free from that bond. Suppose I take this one. Due to thermal agitation, this bond is broken up and the electron becomes free from here. This free electron jumps to this site and the vacancy gets created there. See the movement of the electron and hole. If the electron was moving here, then hole is moving in just opposite direction. Free electrons and hole move in opposite directions. Why mobility of holes is less, that can be explained here. This hole cannot move freely on its own will. Suppose some bond is broken and some electron is transferred here, then only the hole can migrate to that location. That's why we say the mobility of holes is less. The same thing can be felt if their mobility is less. You can think of their effective mass is more as compared to the mass of electron. Now, what happens if we apply electric field? When electric field is applied, these free electrons will try to move from low potential to the high potential, and the holes will try to move from high potential to the low potential. I am writing that here under external electric field. Free electrons move from lower potential to the higher potential, and the holes move from high potential to the low potential or lower potential. That we have already discussed, that their motion will be in the opposite directions. Next point is, under the presence of external electric field, the free electron move from lower energy level to higher energy level in conduction band. Under the presence of external electric field, the holes move from higher energy level to lower energy levels. In the next topic is extrinsic semiconductors. We know that the conductivity of the intrinsic semiconductors is very low at room temperature. So we cannot develop any efficient electronic devices using the intrinsic semiconductors. Hence, there is a necessity for increasing their conductivity, and it can be done by adding few impurity atoms. Whenever a small amount of few impurity atoms, such as few parts per million, are added to the intrinsic semiconductor, its conductivity increases manifold. Such process of deliberate addition of the impurity atoms is known as the doping. The impurity atoms are known as the dopants, and the semiconductor formed is known as the doped semiconductor or the extrinsic semiconductors. There is another name also, the impure semiconductor, because in the pure semiconductor we mixed some impurity atoms. The doped semiconductors can be of two types, the p type and n type. For doping, the size of the impurity atom must be similar to the size of the original atoms of the crystal lattice. Otherwise, there will be a mismatch in the size and it will cause the distortion of the crystal lattice. Silicon belongs to group 14 in the periodic table. Then for doping, we will choose the adjacent elements either from the group 13 or from the group 15. Based on these choices, we can have two type of different doped semiconductors, the N-type semiconductor as well as the P-type semiconductor. How the N-type and P-type semiconductors are formed? If a pentavalent impurity is added to the pure semiconductor, we get the N-type semiconductor, and if a trivalent impurity is added to the pure semiconductor, we get the P-type of the semiconductor. So now we will talk about the N-type semiconductor. A silicon atom is replaced by arsenic, phosphorus or antimony atom here. Pay attention. Earlier the octet was complete and this silicon atom has been removed, and at its location we bring a pentavalent impurity atom. So in the pentavalent impurity atom there will be one extra electron. This extra electron can easily roam as the free electron, because the 4 electrons for that pentavalent atom will go into the covalent bonding, and the 5th one electron will be lightly bound with the nucleus, and by absorbing some energy that electron can easily roam inside the crystal lattice, so that will contribute to the conduction band. It means in such kind of semiconductors the Ne is greater than NH. What will be the electrical charge on the N-type of semiconductors? What do you think? Number of free electrons per meter cube are actually more than the number of holes. The correct answer is that these kind of semiconductors are electrically neutral. Why electrically neutral? If you observe the process very carefully, one silicon atom has been replaced by another arsenic or antimony or phosphorus atom, and we know that atoms are electrically neutral. We are taking out silicon atom and we are putting there the arsenic atom, so the overall crystal remains electrically neutral. For these kind of semiconductor also, at thermal equilibrium we can use the law of mass action. Ne into Nh is equal to Ni square, where Ne again indicates the number of free electrons per unit volume. The current density J is equal to Ne VE multiplied with the electronic charge. The electrical conductivity and electrical resistivity are related like this, inversely proportional of each other, and this in turn equal to Ne mu E into the electronic charge, where mu is the mobility of electrons, V is the velocity of the electrons. One more thing we can write, the Nd is almost equal to Ne. This Nd indicates the donor concentration, and Ne we already know, number of free electrons per unit volume, free electrons per meter. The free electrons are obtained by two sources. We get free electrons by doping as well as by thermal agitation, which breaks the covalent bonds and sets the electron free. But the holes are present only because of thermal agitation. This is the reason that number of holes will be less and number of electrons will be more. And by adjusting the concentration level, the doping level of the pentavalent atoms, we can make Ne much greater as compared to the Nh. Important thing which you should keep in mind, that these type of semiconductors are also electrically neutral. Now let's draw the energy band diagram of the N-type semiconductor. Suppose here we have the valence band. Each energy level in the valence band can have at max 2 electrons. Here is the conduction band. In between the valence band and conduction band, there is the forbidden energy gap Eg. Now, these pentavalent atoms will donate free electron. Every pentavalent atom will donate 1 electron. So, the donor energy levels, they should be close to the conduction band. Here I am making the donor energy level, because these electrons are readily available for the conduction. That's why the donor energy levels are kept very close to the conduction band. This is the energy band diagram for the N-type semiconductor. Now let's talk about the P-type semiconductor. In such semiconductor, the dopant atoms are trivalent, such as boron, aluminium, indium, etc. Let's see it here. We can see pure semiconductor or intrinsic semiconductor. All the atoms are of silicon or germanium. During doping, this silicon atom is replaced by the boron atom. The outer orbit of the boron atom has the 3 electrons, so it will make 3 covalent bonds and one site will be vacant. This vacant site will create 1 extra hole. It means the number of holes here will be greater than the number of free electrons. The holes are obtained by the doping as well as the breaking of covalent bonds due to thermal agitation. While as if we talk of electrons, free electrons are obtained by the breaking of covalent bonds. That's why the number of free electrons will be less. If we look at this structure, then a silicon atom has been replaced by a boron atom, and we know atoms are electrically neutral. So the P-type semiconductor should also be electrically neutral. It's an important information. Whether we talk of intrinsic semiconductor or extrinsic semiconductors, P-type, N-type, pure silicon, pure germanium, they all are electrically neutral. We can write few formulas for numerical calculation purpose. The acceptor concentration is almost equal to the concentration of the holes. The current density formula: N holes, electronic charge, and V hole. The electrical conductivity and electrical resistivity is related by N holes, electronic charge multiplied with mu holes. At thermal equilibrium, the law of mass action will be valid. If we look at this crystal lattice structure, the doping will bring the holes. So free electrons might recombine with the holes. That is also the logic behind the less concentration of the free electrons. That's why this impurity is known as the acceptor impurity. These dopant atoms are known as the acceptor atoms. Since they have to accept 1 valence electron, these holes want to accept 1 valence electron. So the acceptor energy levels should be very close to the valence band. This is acceptor energy level. Now let's take few questions for the numerical practice. Here you can see the question. The ratio of the currents and the drift speeds are given to us, and the question is asking us the ratio of the charge carrier concentrations. So let us start with the solution. We know that electronic current is equal to NEAVE. Similarly, the current due to the holes is equal to NHAVH. According to the question, we have the ratio IE by IH is 3:1 is equal to NE by NH is our requirement. This is what the question is asking to us. So let us calculate. The NE by NH will be equal to 6 by 5, or if you require NH by NE, it will be 5 by 6. This is the answer. Here is the next question, which is asking us the number density of the free electrons. So for solution, we can use the law of mass action. Ne into Nh is equal to Ni square. Our target is Ne, that will be Ni square by Nh. Ni is 1.5 into 10 to power 16 whole square divided by 3 into 10 to power 22. This is equal to 7.5 into 10 to power 9 per meter cube. This is the answer. Here is the next question. A pure silicon crystal has 5 into 10 to power 28 atoms per meter cube, and we are doing the doping with the pentavalent arsenic. The intrinsic charge carrier concentration is already given. We need to find the number of free electrons per unit volume. Let us start the solution. As the doping is done by the pentavalent atom, so we'll get the N-type semiconductor. And for N-type semiconductor, the Ne is equal to the Nd. Nd is the donor concentration, which is given to us as the 1 ppm. We have 5 into 10 to power 28 atoms per meter cube, and in every 10 to power 6 atoms there is 1 atom of pentavalent arsenic present. So basically the Nd will be equal to 5 into 10 to power 28 divided by 1 ppm, which we can write as 10 to power 6 here in the denominator. On computing this, it will become 5 into 10 to power 22. This is Ne. Now at thermal equilibrium, we can use the law of mass action. Ne into Nh is equal to Ni square. So Ne is 5 into 10 to power 22. Nh is unknown. Ni is available. 1.5 into 10 to power 16 whole square. Nh comes out to be 4.5 into 10 to power 9 per meter cube. Let's have the next question. It's a good one. The number of silicon atoms are 5 into 10 to power 28 per meter cube, and it is doped simultaneously with the arsenic as well as the indium. The question is asking Ne, Nh and the type of the material. Looking at the language of the question, if we focus on the doping concentrations, here for arsenic it is 10 to power 22, and for indium it is 10 to power 20. It means the arsenic, the pentavalent impurity atoms are dominant. So the material should be N-type. First answer is clear and easy. The material is N-type semiconductor because this density is more. Now we go for further calculation of Ne and NH. Let us look for Ne. The free electrons are contributed by the thermal agitations as well as due to the doping of arsenic. The free electrons we get via two methods: by thermal agitation and by doping with arsenic. Both data, if we compare, by thermal agitation, the intrinsic charge carrier density will give you the idea. It is around 10 to power 16 per meter cube. And with the arsenic doping, it is around 10 to power 22 electrons per meter cube. So basically this data is more. Each arsenic atom donates one free electron. So for calculation purpose, we'll consider this only and we can neglect it. Ne will be equal to 5 into 10 to power 22 because of the presence of arsenic, but here is indium also present, which will bring the holes. So there will be the recombination of the electron and holes, and the effect should be written as 5 into 10 to power 20. When we do this calculation, it comes out to be 4.95 into 10 to power 22 per meter cube. After getting Ne, we can easily calculate NH by law of mass action. Ne into NH is equal to Ni square. So the NH should be equal to Ni square divided by Ne. Ni is given to us 1.5 into 10 to power 16 whole square, and Ne is 4.95 into 10 to power 22. When we compute this number, it comes out to be 4.95 into 10 to power 9 per meter cube. Let us start the solution. For creation of hole in valence band, an electron from valence band must gain sufficient energy to jump into one of the acceptor energy levels. Hence, the Hc by lambda should be greater than or equal to 57 milli electron volt. Let us put up the values. The unit electron volt is getting cancelled out here. Our target is the lambda. This will give you the lambda maximum is equal to 2.18 into 10 to power minus 5 meter. Here is the next question. We have to calculate the conductivity and resistivity of an N-type semiconductor. It's a simple formula based question. So let us proceed with the solution part. The formula for the conductivity sigma is known to us. It is electronic charge multiplied with Ne mu E plus NH mu H. The electronic charge is known to us 1.6 into 10 to power minus 19. Ne is 8 into 10 to power 13. Here is centimeter cube. We will convert this data into the meter cube. So here I should write extra 10 to power 6, as we know that 100 centimeter makes 1 meter or 1 centimeter is equal to 10 to power minus 2 meter, and 1 centimeter cube is equal to 10 to power minus 2 meter cube. So wherever the centimeter is present, we will convert that into the meter because we want the answers in the SI units. Next, mu E. Mu E is 2.3 into 10 to power 4 centimeter square, means 10 to power minus 4 meter square, plus NH. NH is 5 into 10 to power 12, and per centimeter cube we will convert to per meter cube. So here I should write extra 10 to power 6. Then mu H is 100 into 10 to power minus 4. Let's do further calculation. On computing this entire data set, the answer will come out to be 29.448 ohm meter. And the resistivity is inversely proportional to the conductivity. So for resistivity, we should put it as 1 upon 29.448 ohm meter. And this will become 0.03 meter inverse. This is the final answer. Let's start the solution. Before doping, we know that Ne is equal to NH is equal to Ni. So the number of charge carriers per meter cube will be equal to 7 into 10 to power 15. This is the concentration of the free electrons per meter cube, plus the number of holes per meter cube is also same. So 7 into 10 to power